Compute Express Link. Jim Pappas is a speaker for the session, and he is no stranger to the industry. He's founded or has served on multiple organizations: PCI SIG, USB SNIA, IBTA, our own very OFA, the Green Grid, Compute Express Link now, and many others. He is currently the Director of Technology Initiatives at Intel, with the responsibility to establish broad industry ecosystem that comply with new technologies in the area of enterprise I/O, energy efficient computing, solid state storage, and persistent memory. Jim has over 30 years experience in computer industry and holds 8 US patents. Jim, your mic is open now. Thank you for joining us, and we can't wait to hear about Compute Express Link.
Thank you, Divya. Am I coming through okay?
Yes, you are.
Perfect. Okay, and first of all, I am delighted to be here today. Thank you for inviting me. And I have very deep feelings for Open Fabrics Alliance. It is almost 16 years old to the day, and I called a meeting 16 years ago, to almost to the day, and as a result of that meeting, Open Fabric, what is now known as Open Fabrics, was born. And Jim Ryan did most of the work, but I've been involved with this thing from the beginning, and I absolutely love OFA. So today I'm going to talk to you about CXL. I am the chairman of the CXL Consortium, and I'm a director at Intel. And I have a lot of slides, and I can only give you a pretty high-level overview in the 30 minutes that I have. I will say that we just did 3 full days of recorded training for CXL members, and the CXL 1.1 spec, which has been available now for about a year. There's 2 of the days of training are for the CXL 1.1 spec, and we're about to make that public, available through the CXL website. So you will be able to get as much information you want about CXL 1.1 through that training. There was a second day of training that goes into CXL 2.0. We will not be talking about CXL 2.0 because right now that's confidential to the working groups that are finishing up the design. They are very close to closing the 0.9 rev of the spec, and that should be complete within a quarter. So, however, any company that's a contributor member of CXL could also get the CXL 2.0 training. All that training isn't quite on the website yet, but it will be there very soon. So, with that, next slide, please. I tried using my control here, but I guess I'm not in control of the slides. So this is the agenda, and we'll go through each of these sections one by one. So next slide, please. Why are we doing CXL? Well, there's, if I had to put one word on it, it would be CXL is there to really drive heterogeneous computing. And where's that coming from? These 3 areas that I'm showing here, no surprises here to anybody. This is where much of the innovation in computing is happening. And fabrics, of course, are a big part of that as well. So CXL will enable new types of fabrics or new capabilities into existing fabrics by the method that those fabrics attach into the CPU. Next slide, please. So we spend a little bit of time on this slide here. And if you look at the 2 diagrams on the right, let's start with the top one first. So focusing on that top picture, that's what today's environment looks like in a heterogeneous computing world. And we're taking a very memory-focused view here. So at the very top of the thing, you have memory that's attached to the CPU. And at the bottom, you have memory that is attached to accelerators. And right now they are, there's certainly 2 different domains. And now the 3 things across the middle. On the left, you have a bank of CPUs, some number of CPUs. In the middle, you have some number of accelerators, and those could be GPUs, FPGAs, AI accelerators, custom logic, etc. And then to the right, you have PCI devices. You know, those would be like, we're showing some NICs here, but those could be NVMe devices, etc. So what we're trying to talk about in this is, how do each of these classes of devices talk to the memory it's in the CPU versus the memory that's in the accelerator? And in all three cases, you could see that it's different mechanisms depending on which bank of memory you're talking about. So for the CPU, to its own attached memory, of course, it's got write back cache memory. And if you look at how it connects to the bottom to the accelerator memory, well, it has to go through the accelerator, and there'd be uncached memory to whatever access the accelerator allows. Now, if you look at the accelerators in the middle, of course, they have load store access to their own local memory, but to get to the CPU memory, they would use PCI Express DMA. And by the way, the red coloring indicates that it's a different mechanism than the mechanism to its own local memory. Similarly, the CPU had the same color scheme applied. And finally, if you look over at the PCI devices, it would use PCI Express DMA access to the CPU attached memory, but the best it would probably get is PCI peer-to-peer access to the accelerator memory. So that's the world today with PCI Express. If we look at what happens once we bring in CXL, and CXL is a memory-centric architecture. It brings memory access and memory semantics to adding it to what was traditionally only an I/O bus. So if we start with the CPUs, it has cacheable memory, both north and south, both to its own memory and to the accelerator memory. Likewise, the accelerator has exactly that same capability as well. And the PCI devices, the PCI DMA access that it had to the CPU memory now also has it to the accelerator memory. So you get the symmetric capability to both portions of memory. And we'll talk about this later. All of that memory that is attached to the accelerators in the middle will be could be mapped into the coherent memory space of the CPUs that it's attached to. So that memory could be used as part of the overall set of memory that both the CPU and the GPU are attached to. In many ways, it's very, very similar if you think about a dual processor system, and I'm keeping it two processors just for simplicity, where you have two processors connected with a coherent link, and that varies by manufacturer. What you could do with a dual processor system, to the first order, you could do exactly the same thing with these accelerators. So we're bringing a lot more capabilities to this accelerator ecosystem. Next slide, please. A lot of the stuff here I've just talked about, and but a couple of things. We build this on top of PCI Express. We're using the exact same wires as PCI Express. And newer versions of PCI Express have introduced a new capability called alternate protocol, and we take advantage of that. So when the device first powers up, it identifies itself of being capable to use the alternate protocol called CXL, and PCI Express is then shut off, and CXL replaces the protocol. And this is what gives us that much lower latency, memory class latency versus IO class latency. And it duplicates the functionality of PCI Express, but adds new capabilities, and we'll get that coming up very, very soon. And it's a fully open industry standard. It's no surprise CXL 1.1 was donated by Intel, and we decided to make this as open as any standard that we've ever done. I've personally been involved, was responsible for the original PCI bus and its replacement PCI Express, and I was also Mr. USB. And those were specs that were initiated by Intel. We donated them to the industry. Of course, we participate in their evolution, but these specs are owned by the industry. And CXL is in that exact same space now. We donated the 1.1 spec, but we have multiple companies. Any company can join and participate and drive the direction of CXL. So Intel, although we donated the spec, we have one vote on the direction of the spec, just like any other company out there. So anyway, let's move forward to the next slide. Here's the, this is, I'm going to spend just a brief period of time here. There were 9 of these companies were the original founders of CXL when we put together the initial working group just over a year ago. In September, we incorporated and we expanded the board to the 14 companies that you see here. Of course, Intel was part of this from the beginning, but there's something I think that's significant here, and that is that when it comes to coherent interfaces, I don't think you could point to any time that 2 different CPU companies agreed on a single coherent interface, and certainly across 2 different architectures. And when we incorporated, each company had, each of the board member companies had a vote to who to bring onto the board. There were 19 companies looking for the 4 spots. We ultimately brought in 5, but 3 of them that are important is that we brought in AMD, ARM, and IBM Power. And I think that this is historic because in the past, as I said, no 2 CPU companies have agreed on a single coherent interface. And now we have, almost the entire computer industry is agreeing on CXL. So that was a very, very significant effort. We also brought in Microchip and Xilinx at the same time. We also this also brought together, we already had a very, very close working relationship with Gen Z. Xilinx are the pen holder and the lead company for C6, and IBM, of course, for OpenCAPI. And we brought the principals, the actual people who are responsible for those are sitting on the CXL board now. So we see this as a really great convergence point, and it's an important element to ensure the success of creating the ecosystem. And at the end of the day, what really matters on any new standard is what's the ecosystem that develops. So next slide, please. Okay, so, excuse me. It's not a COVID-19 cough, by the way. So if you look at this diagram, CXL fits in that node level layer of the interconnect architecture, which is what you normally see at more or less a board level, a chip-to-chip interconnect, typically at a board level. Sometimes it goes board to board. Some people have done partial racks with the PCI. And so if you, in your mind, think of what does PCI do, and CXL, at least in its current definition, has the same scale. And I don't know of any kind of plans to move CXL out of that type of scale. The previous talk was on Gen Z. We have a great relationship with Gen Z. We have a formal agreement between the 2 organizations. And the intent there is to allow Gen Z to attach to CXL very, very efficiently. And any fabric that is going to use memory semantics probably needs a coherent interface to the CPU if you want it to work reliably. It's pretty much a requirement. So it just makes sense for us to have that great relationship with Gen Z. Gen Z is more at the rack level and at the row level. So Gen Z in this diagram would be sitting above the CXL. Okay, next slide, please. Now we're going to start getting into more of the meat of CXL specifically. This diagram introduces what's called FlexBus. So you see the microprocessor there, and you see that there's a PCI channel connecting, in this case, to a connector. And you see two different cards. One's a PCIe card and one's a CXL card. You would be able to take either of those cards and plug them into the same connector, and they would operate either as a PCI device or a CXL device. So CXL utilizes the exact same wires of PCI Express and works cooperatively with PCI Express in that alternate protocol extension that's newly available to PCI Express. Our first generation works on PCI Express Gen 5, which is 32 gigabits per second. And we are aggressively moving towards PCI 6, which would double the bandwidth once again. So next slide, please. Okay, here's a diagram. On the right-hand side is the accelerator. On the left-hand side is the host processor, and the performance that you would see across those two for memory type of operations would be very, very similar if these were two host processors in like a dual processor server. An important point here is you see that there's memory in the middle between the two. There's host memory that's attached to the CPU, and there's optionally there's device memory that's attached to the accelerator. Those two memory pools would be part of the coherent memory pool that's addressable by both machines. There are three protocols that will be running over the CXL link. So initially it was a PCI link. We switched to the alternate protocol, and the first one is CXL.io, which essentially duplicates PCI Express Gen 5. Then the two new ones are CXL.cache and CXL.memory. And those are memory, those both have memory semantics, and we'll go through later how those are used. Those three protocols can be dynamically multiplexed over the wire. So on a packet by packet basis, they could be any one of the three protocols. Okay, next slide, please. And one more. Okay, here we have, I'm going to focus on the diagram to the left. I talked earlier about the three types of transactions: CXL.cache, CXL.memory, and CXL.io. And if you look at the left side of that center diagram, you see in blue is the PCI, that's PCI Express Gen 5. And to the right of it is CXL, the CXL.io module. So you see that it's duplicating the functionality of PCI Express Gen 5. The big difference is PCI Express Gen 5, I'm sorry, is statically attached, at power up is statically attached to the pins. And it's not capable of dynamically multiplexing. The CXL .io in green, adjacent to it, is capable of being dynamically multiplexed with the two other protocols. And then to the right of that, you see the CXL.cache and CXL.memory transaction and link layers. And those are the mechanisms that do that very low latency .io memory semantic transactions over the pins, and the relative thin width of those versus the link layer is representative of lower latency. Next slide, please. So this is going to be a blow up of that diagram we were looking at, and so this is just showing those two are designed specifically to do very, very low latency access, and good enough that we could put memory off on this interface and add it to the memory that's available to the systems. I'm not going to go through all the framing and the flits and those types of things that occur. So why don't we move on to the next slide, because you can get all that through the training. So one of the things that is really unique about CXL, and one of the things that I think is going to be perhaps the most important thing that's going to make CXL succeed, is what we call asymmetric complexity. If you look on the left-hand side, that could be, for instance, a dual processor system, or an accelerator that is using a full symmetric CCI interface, cache coherent interface. So in there, that center section, the caching agent and the home agent, are probably the most complex areas of the CPU. That's where compute, memory, storage, caching all comes together, and coordination of that is I don't know, probably the best word is horrible in terms of difficulty. I've got experience, my team, with my own company's cache coherent interface. I'm not going to talk about that. I'm talking for the association here, but we did some selective licensing on that, and many companies were interested. And I would say that about 0%, rounds to 0% of the people who tried to build accelerators that had a full coherent interface succeeded in getting parts to market. It's just too complex. You have all of the complexity of all that tough complexity that goes into a CPU, plus everything you're trying to do on an accelerator. So if you look to the right, this is what it's like with CXL. And so you can see that the caching agent and home agent is missing in the accelerator. We've made that very, very simple. And we did that on purpose, because that's what it's really going to take for this ecosystem to really evolve, so that many companies will be able to build devices and actually be able to get them to market. And it utilizes the capability that's in the adjacent CPU. As an analogy, when we started USB, I'm just to plant this kind of concept in your head. We said we wanted to have a interface that was simple, because we realized that we had a full PC, a desktop PC sitting there with a lot of capabilities, and the devices that would attach to it, like printers and scanners, were less complicated than the PC was. And in fact, our target was, we wanted that interface to be so asymmetric, the complexity, that we wanted to be able to win the mouse. If we didn't win the mouse, we felt that we lost. And we took that to heart. And that, there were other technologies that were more symmetric, equal complexity. So you'd be able to, if you had a printer and a scanner attached, even if the CPU was off, you'd be able to push the copy button and have it happen. Well, guess what? Those technologies did not succeed. USB, in its simplicity, was able to really drive the ecosystem. So just thinking of that model. Now, obviously, we're not going to be building mice on CXL. That's not what I'm trying to say. But that concept of splitting up the complexity and taking advantage of the complexity that's inherent in the CPU and not duplicating that in the accelerator is a key area. So going on to the next slide is an example. I can spend the full 30 minutes on this one slide, and we're not going to, of course. That center picture here is that same picture that I showed before, that asymmetric symmetry between the accelerator and the CPU. But what you see is that it could be used in actually two different modes. So on a page-by-page basis, the accelerator could choose how to treat the memory that's attached to it. So if we look to the extreme left, that's what we call, and we call this bias, by the way. So there's device bias and host bias. So on the left-hand side, there's a device bias. So let's say that there are pages of memory that the CPU, that the accelerator rather, is really using as local memory, but you still want to have the CPU to have access to it. Then the accelerator could just use that as local memory. It doesn't affect any of the caching that goes on, doesn't affect caching. And then anytime the CPU would want to access that, it would have to go back and not use the data, any data that was cached, but go off and use the local copy of the memory. And that's to give, if you think about the kinds of workloads that happen in accelerators, the accelerators are actually purpose-built in order to handle that workload. So the application knows exactly what kind of access is being used for for each page of memory. So it can make a decision saying, this is something that I'm going to use it 99% of the time. So let's give this thing device bias. If it's something that is more equally used or more shared, then you would use host bias. And then the accelerator simply uses the coherence engine that's in the CPU to ensure cache coherency. So but irrespective of which mechanism, whether it's device or host bias, no matter which one was selected, cache coherency and consistency is guaranteed. You can't make a bad decision that would cause corruption of data. It'll always work. The question is do you want to get extra performance by this? So that's all I'm going to say. You could go to the training and get much, much more information on this. So next slide, please. So finally, the use cases. We have about 11 minutes left. So this is a very important slide. So we have defined currently with CXL 2.0, this will get more complex, but CXL 1.1, we have 3 types of devices. We call them type 1, type 2, and type 3 devices. So a type 1 device would be an accelerator. So in all 3 of these cases, by the way, you can see at the bottom there's a processor. And in all 3 cases, the processor has local memory attached through a memory interface, DDR interface. Attached to these are the accelerator. So the type 1 device on the left-hand side would be a device that has its cache for its its working set, but does not have attached memory, or certainly does not have attached memory that it wants to contribute to the overall basically NUMA domain here of the processor, of the attached processor. So in this case, it would use CXL.io for all of its I/O operations. By the way, CXL.io is always used in CXL, so you must implement CXL.io. But it does support CXL.cache, and that cache could be so that accelerator now has full access to the DDR memory in the processor and could cache that. And cache coherency is guaranteed with the host processor. So it's using system memory and it's cached, and that cache is coherent. In the center section, this one is the same type of accelerator, except in this case, there's accelerator attached memory. And that memory is now part of the overall memory coherency of the system. And now they're really, this is very, very similar to a dual processor system where both processors have its own memory, and that memory is shared and cache coherent. The difference, of course, is that the accelerator is designed, specifically to accelerate parts of the application. So in this case, you have to use all 3 protocols. I/O, that's always required. You have .cache and .mem. And then finally, the type 3 device on the right-hand side. This one is a different type of accelerator. It's not really an accelerator at all, but think of it as we're calling it a memory buffer here, but think of it as a memory controller. So if you wanted to add more memory to the system, and this could be DRAM, so you could have much more available DRAM in the system, or it could be persistent memory. To have, to bring in lots and lots of persistent memory into the system. This moves persistent memory off of the DDR interface, which isn't, honestly, is not the best place to put it. Because to some extent, persistent memory, it's logical that as you would add persistent memory to the system in a new memory tier, you'd probably want to be increasing DRAM, primary memory at the same time at the same rate. But of course, if they're sharing the DDR bus, as you add persistent memory, you're doing it at the expense of regular memory. So here we're allowing more memory, whether it be DRAM or persistent memory, to be added, and for memory expansion. So that memory buffer is more than just a buffer. It's really like a memory controller. And that's what we call a type 3 device. And all of that memory would be, logically no different than if it was attached to more DDR channels on the microprocessor. Okay, moving on. So this is the first diagram that I showed you, where we talked about how, we have two sets of memory. We have microprocessor attached memory, and we have accelerator attached memory, and how through the mechanisms that CXL adds to the existing PCI Express wires, through the new protocols, really makes this a very, very symmetric environment, and really opens up the world for heterogeneous computing. Will really be a big advancement, and everything, no matter what type of device, it's symmetric access both north and south here. So if you move on to the next slide, I think this might be about the last slide. So in summary, we've added coherency to existing I/O buses. It's very performant, extreme low latency. By the way, the type of performance that you could expect to see over CXL would be the same level of performance. It's not going to be exact, but certainly we are expecting, and it's also going to be implementation dependent. But if, the type of performance that you would see processor to processor in a dual processor system, you could expect to see in a CXL enabled, processor and accelerator system. We have that asymmetric complexity, which really is key to establishing a broad ecosystem. And of course, it's an open industry standard, and any company is free to participate. So next slide. And that was it. So we have 4 minutes if anybody has any questions. I will also plan to go to the Birds of the Feather session as well later.
Sure. Jim, there is a question coming in. Are you able to speak at all to what that might imply about Intel's perspective on the role of PCIe Gen 4 over the next year or two? This is from Nick Gold. Nick, I am going to open your mic in case you want to ask follow-up questions.
You can't speak to roadmap.
My role at Intel is to drive technology initiatives, not to drive Intel products. I lead many industry consortiums, and to some extent, my separation from Intel products is what gives the industry enough trust to trust me to lead industry consortiums. If I was an Intel product manager, as an example, I wouldn't trust me to run industry consortiums, but I keep myself out of that. Now, to that extent, my organization does enable the industry to attach their devices through these industry standards to Intel products. So we are dedicated to PCI Express Gen 4, we have a very aggressive roadmap from PCI Express Gen 4, which I believe we've publicly said is coming out, in the next generation of products. And we are, but we have a very rapid transition from Gen 4 to Gen 5 to Gen 6. And in there, from CXL.1 to CXL.2, from CXL 1.0 to 2.0 and 3.0. The CXL consortium, 1.1 is out there. 2.0 is at approximately the 0.9 level. It's going into 0.9 review within a couple of weeks, and the planning is starting already for CXL 3.0. And each of these are going to be significant steps up. One thing that is I'm going to state that this is also very, very important to understand. I'm going to give a special kudos to the PCI SIG. PCI has done a spectacular job in making sure that backwards compatibility is ensured from one generation to the next. So you could take a PCI Express Gen 4 card and plug it into a PCI Express Gen 1 system and expect it to work. And vice versa. You could take a .1 card and plug it into a .4 card. That is another very important dynamic that helps people invest in the technology because you get investment protection. And CXL is taking that same approach. In fact, we even put into our bylaws that it takes a very, very high threshold, a special threshold of voting, near unanimous, to come out with a specification that's not backwards compatible. And we did that because that PCI Express example I said is almost unprecedented. It's spectacular.
Thank you, Jim.
Let me answer your question, because I'm not going to talk about Intel's products on a CXL presentation, but I did.
Actually, you did. CXL does rely on PCIe and is backward compatible. So I think that's good information, Jim, for this context. Yeah, thank you.
Anything else?
Other questions? Feel free to submit using the Q&A panel or even raise your hand just to ask verbally real time.
Well, it's 9:30, so.
Yeah, I guess not, Jim.
I ended on time.
Yes.
And let's see, Divya's laughing there. She didn't trust me. It's good. By the way, Divya works for me, so having employees who don't, who feel empowered to challenge your manager is good. So anyway, once again, thanks for inviting me. As I said, I feel extremely committed to Open Fabrics. It's one of my favorite initiatives ever. And so feel free to invite me again. Once again, the training, we just did a 3-day training for CXL members, 3 full days of training, or they're 3/4 days or something. It's a lot of material. We go into the material here in excruciating detail. So those of you who are interested are able to get access to that. It is going public very, very soon. I don't know the exact, I know that they're just putting like a little disclaimer, in the front of the videos, and they're in the process of doing that now. So I would expect it's a week or two probably, and it's going to be available on the CXL website. So to get information. So thank you very much.
Thank you, Jim. Jim, you'll be joining us to the Birds of the Feather session that begins in about 30 minutes. We have a break time here. So yeah, feel free to stay on, or you can join us back. Just a word about Birds of the Feather. The discussion, unlike other sessions,